This is section 5.2, the definite integral. We're going to learn to find the precise net area under the curve using Riemann sums, which, as we alluded to last time, was infinitely many rectangles under the curve. We find each of their areas. We do this by taking a limit of the number of rectangles, and we add up each of their length times widths. Let's look at an example. To find the precise area under this curve, let's first use the geometry trick so that we can verify our answer when we use Riemann sums. So we have a curve. It looks something like this. This is not completely to scale, but it looks something like this. Okay? And if you take a look, you'll notice that this is actually a trapezoid. Right? It's a trapezoid, and we know the area of a trapezoid, right? The area is length 1 plus length 2 divided by 2 times our width, right? So it turns out, right, the area is going to equal L1 plus L2 all over 2 times the width, which equals, what is L1? What is L2? Well, L1 is f of 2. L2 is f of 7. Divided by 2. And then times our width. What's our width? That's just 7 minus 2. Okay? So we wind up doing this out. Let me actually do it over here. This is going to equal, well, f of 2 is going to be 4 times 2 plus 3. And f of 7 is going to be 4 times 7 plus 3, all over 2, times 5. And then this is going to be 11 plus 31 over 2 times 5. And then this is going to wind up being 105. Okay? So that's the precise area under the curve. That's the precise area under the curve. Maybe I could actually organize this a little bit better. All right, so that's our answer, 105. Now, what if we didn't have a nice straight line? What if we had some fancy curve like that, right? We wouldn't get to use this geometric trick. We would have to use Riemann sums. So let's do this out. This means taking a limit, doing a bunch of simplification, and using a fancy identity, or not super fancy, but a counting trick that I will give you on a quiz or an exam, just to be clear. Anyway, as the book notes, it doesn't matter whether we use left or right-hand endpoints, but it's easiest to use right endpoints, so that's what we're going to do. The rectangle width, right, is always the same. Right, it's delta x, it's b minus a over n. So it's going to be 5 over n in our case, right? And so the area of our rectangle, or sorry, the area of all of our rectangles, right, it's going to be an infinite sum. Let me just quickly illustrate what's going on here, right? We've got this curve, right? And so for the first rectangle, this is just kind of a illustration, right? It's arbitrarily thin, but we would find the height of that rectangle, right, using right endpoints. Then we would find the height of the second rectangle, right, with the same width, and we would just keep doing this, and then we would eventually find the height of that last rectangle, and then, you know, find the width of that, you know, right, and pretend that they all have the same width, right? So that's what we're doing. Okay, so the area is going to be f of, again, now what's the first right endpoint? Well, it's going to be 2 plus delta x, which is 5 over n, plus, and then just to illustrate what the second term would be, it's f of 2 plus, and that's going to be 2 times 5 over n, 2 times delta x, right? Let me actually rewrite 5 over n as delta x, just to make this crystal clear. Right? Because we're moving one width to the right each time. And so then the last one is going to be 2 plus n times delta x, right? And that's the sum of all the heights. And we're multiplying all of that by delta x, right? Remember that trick where, we factor out the width, right, from last time. Okay? So if we do this out, we just wind up getting, right, I'll just do this one more, right? 2 plus 5 over n, f of 2 plus 5 over n, plus f of 2 plus 2 times 5 over n, plus blah, 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 f of 2 plus n times 5 over n, and then all of this is times 5 over n. So now if we actually plug in these guys into f of x, we're going to see what we get, right? But just to point out really quickly, this right here corresponds to this height. Oh, that's way too much. This height for that first rectangle there. Okay. Let's try to get a little bit thinner there. That rectangle, okay? And I guess this guy right here corresponds to this rectangle here. And then the last guy over here corresponds to this rectangle there. Okay? Just so we can see where we're going with all this. Okay, anyway, plug this all in, and we get 4 times 2 plus 5 over n plus 3. I'm going to go ahead and forget about the second. Well, no, I'll keep the second term. It's going to be 4 times 2 plus 2 times 5 over n plus 3 plus blah, 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 plus 4 times 2 plus n times 5 over n plus 3. And then all of that's being multiplied by 5 over n. Okay. Bunch of algebra at this point. I'm just going to multiply these two together, add this, multiply these two together, add this, multiply these two together. Whoop. Add this. Okay, let's see what we get. It's going to be, draw this down here a little bit, 11 plus, and then I'll also multiply out the other stuff, 20 over n, plus 11 plus, and this is going to be 2 times 20 over n. See where I'm getting the 20 over n from, right? That's this times this, this times this. But you see how I had that 2 here? Okay. We keep doing this. And then this winds up being 11 plus n times 20 over n. All times 5 over n. Yes, I know we could just simplify that to 20 right here, but we're just going to keep it because we want to establish a pattern, right? Now at this point, I'm just going to combine a bunch of terms, okay? How many times am I adding the number 11? 1, 2, etc. n number of times, right? So I'm going to write this as 11 times n, right? Because that's the number of times I'm adding them together. So I'm going to group all of these 11s and just write it as 11 times n. Now, with the 20 over n, how many times am I adding that? Well, let's see. We've got 20 over n plus 2 times 20 over n plus blah, 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 plus n times 20 over n. And this is all times 5 over n, right? So that's n terms also. So I guess what we could do is we could distribute a little bit and get 11n times 5 over n plus, and I guess I could factor out the 20 over n, couldn't I? I could get 1 plus 2 plus blah, 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 plus n times 20 over n times 5 over n. Okay? And maybe you notice, oh, look, the n's cancel there. But what's going on over here? Well, it turns out This is not something you should have known, but if you take a class called discrete math, then you can prove this using induction. You also, maybe you saw it in pre-calc or something. You can substitute for this value right here. There is a nice little counting trick. That's when I talked about a counting trick earlier. That's what I meant. So the first term I hope we see is going to be just 55. It turns out 1 plus 2 plus 3, etc. winds up being n times n plus 1 all over 2. And then this winds up being times 100 over n squared, right? So kind of weird, but this became this. That is not something I would expect you to know. I will give that to you on a quiz or an exam. But that's what we've got. Okay? Anyway, when you do this out, right, you can notice, hey, the 2 cancels kind of nicely with the 100 to leave 50. And when you take this limit, oh, shoot. So what we did here was we just, we did this for an arbitrary n, but one thing I actually neglected to do is say, hey, wait a minute, what happens when we take this limit as n, as n approaches infinity? Right, so everything we can do, we can say, well, hold on a second. What if we stick in here this limit as n approaches infinity? Limit as n approaches infinity. Limit as n approaches infinity. And when we take this limit, we see that we get 55 plus 50, or 105. So sure enough, our answer here corresponds to our answer there because it's the same thing. We just use a different method. Okay? So that's how you do this problem. Is this problem a mess? Yes. Did it take a long time? Yes. Did we need an identity that we didn't use before? Yes, but again, I'll give that to you. We won't have to do this for very long. But I do want to show you, this is how you find the area under the curve. This is a precise way to do it. By taking a limit of the sum of the areas of the rectangle. Of the rectangles, right? Now, remember, before, we looked at the curve y equals x squared, right? Not just, mx plus b. How would we do this? Well, if we set it up the same way, it would be area equals a limit as n approaches infinity of, let's see what it would be. It would be, I guess, f of 0 plus delta x plus blah, 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 plus f of 0 plus n delta x times delta x, which in this case, just to write it out a little bit more, would be limit as n approaches infinity of, I guess it would be 0 plus delta x quantity squared plus blah, 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 plus 0 plus n delta x quantity squared, all times delta x. And delta x would actually just be 2 over n, right? I guess we know that much. Okay. But this would be quite a bit to write out, right? We'd have to factor each term, write it all out. So we're gonna shorten this notation a little bit using something called sigma notation, right? So the sigma, right, means the sum from I to n, right? And the idea is that this is cataloging n different terms that are being added. So for example, this sigma notation right here would be 5 times 1 squared plus 2 plus 5 times 2 squared plus 2. See how the index is kind of ticking off each time? And you just keep doing this out. You just keep doing all that. It works both ways, right? If I'm trying to interpret what this means, this is what it means, right? But if I wanted to write something big and long like this, I guess I could have done this. The sum from I equals 1 to n of 2n minus 1. Or sorry, the sum from 1 to 5 of 2I minus 1. Sorry about that. There we go. Okay, so instead of writing all of this, we could write it like this. The sum from I equals 1 to n of f of 2 plus I times 5 over n. And then times 5 over n. So this is just a much more compact, condensed way of writing this. Okay? So, looking at this parabola problem, right? We're getting the delta x equals 2 minus 0 over n, which is 2 over n. Let's see what we wind up getting. The area is going to equal the limit as n approaches infinity so let's write this. Let's write it this way one more time. F of 0, or I guess we'll skip that. Let me actually just copy stuff over, right? I'll just copy this over because I started it. Copy. Well, make sure we copy that. There we go. There we go. And then instead of writing it like that, why don't we write it as the limit as n approaches infinity of the sum from 1 to n of 0 plus I times 2 over n squared times 2 over n. All right? So when we do this out, what we're going to do, we're going to keep this annoying sigma here, right? I know it's a lot to write down, but we're just going to keep it here. We're going to foil this out, right? We're going to foil this out, and we wind up getting 0 plus, well, I guess the 0 goes away, doesn't it? Right? Plus 0 plus, I guess this last term is going to wind up being I squared times 4, times 4 over n squared. And all this is times 2 over n. I guess that kind of worked out nicely, didn't it? Right? If we multiply through by the 2 over n, we get I squared times 8 over n cubed. Okay? And I guess if we wanted to, if we took note, we could note that this is really its own thing, right? That's the only part that depends on I. We could factor out the 8 over n cubed. And at this point, we need an identity. And again, I would give this to you, because there's no way I would expect you to know this or even to memorize it. But it turns out that this equals this. Again, would not expect you to know that, but that's what we get. It turns out, again, you can use something called induction to show this. And so anyway, when you take this limit, right, we notice that we've got a factor of 2 up there, we've got an 8 up there, and we've got a 6 down here. So we get 16 over 6, or 8 over 3. And if you remember, in the previous lecture, I did say that the area was 8 over 3. So that is, in fact, the right answer. Now, I got it pretty quickly, so maybe there's a shortcut I'm not telling you about.